It's my prime pleasure to introduce Elliot Owen. When you work with Elliot, as everybody sure knows, you end up learning so much yourself from what he does. You're going to learn a lot today. Elliot, what yours?
Thank you very much. Mr. Wisdom is correct. My name is Elliot Owen, and I'm here to tell you a story today about Elon Musk's crazy latest idea, the Hyperloop. I'll begin by describing, what it is and why it should be built. I'll analyze the 4 main reasons why it's different from all other forms of transportation. I'll describe how I replicated those forms, those 4 features, in my own prototype, show you some test footage, and then I'll try to analyze, what are the things that I learned at the small scale could be applied to a real Hyperloop. Afterwards, at 6 o'clock, there's going to be a live demonstration in Mr. Wisdom's room. I encourage you to come to that, and then go to the other presentations happening in the theater afterwards. So, what is the Hyperloop? It is a way of getting from the Columbia Bridge, San Francisco to LA in 35 minutes. It goes extremely fast. And it does that because it has some very, very special features. It travels at between 300 to 700 miles per hour. So, what really is this idea? It seems kind of really strange. Elon Musk builds it as a 5th form of transportation, completely unique and distinct from automobiles, trains, planes, and boats, but having some of the best features of each. Besides being fast, it's extremely efficient. But the world had no idea what this was until last August, during the summer. Elon Musk actually released a 54-page white paper telling everyone what it actually was. I read it and decided this is the perfect thing to do for my senior project. Scientists have looked at it, they haven't found any major problems with it, although it's been out for a few months now. However, it hasn't actually been prototyped at any scale. So I figured, this is what I should do in order to graduate. Okay, but what is it? In order to move very quickly, you have to be in a special environment, specifically an evacuated tube. Evacuated doesn't mean vacuum, that's very hard to do, but just low pressure, about 1/10,000th of atmospheric pressure, which is actually quite reasonable given industrial scale vacuum pumps. So you have 2 of these tubes traveling back and forth that have low pressure. Low pressure means low air resistance, and you can travel quickly and efficiently. So, one of the interesting things is that those lozenge-shaped capsules don't actually power themselves. They coast almost all the way, which is quite unusual for a form of transportation. So they're going to be coasting at between 300 and 700 miles per hour. How did they get going that fast in the first place? Well, you use what's called a linear induction motor, or that's what Elon Musk proposes. I expanded the definition to be any form of electromagnetic launch. It seems kind of arcane, but you've actually probably experienced this if you've ever been on an industrial-grade minecart or on a roller coaster. The same kind of technology that propels them. And these have been proven to work at the high energies required for the Hyperloop. So, this thing accelerates you, you go winging along, you're moving fine. What keeps you from crashing into the bottom? Elon Musk points out in his white paper, wheels don't work at that kind of speed. They simply evaporate, burn up, be very inefficient. So how do you keep yourself from impacting the bottom? He suggests something called an air bearing. Basically, you take 2 sheets of material, very, very thin gap between them, and you pump high-pressure air in that gap. That creates an extremely slippery and remarkably stiff film of air that allows you to coast at very, very high speeds. Again, it seems like a kind of a strange technology, but you've experienced this if you played on an air hockey table. Flat sheet of plastic, a lot of small holes releasing a small amount of air. When your puck goes over it, it traps some of those air holes and creates a little film under. Same principle that makes hovercrafts work. So here we are. We're moving very fast on a slippery sheet of air. Seems all well and dandy. But then you encounter the Cantor's limit, which we all know and love. Right. You can think of it as the syringe effect. If you close off the end of the syringe and you try to move it really fast, you're going to encounter a lot of problems. Even if you evacuated a 350-mile-long tube to 1/10,000th of atmospheric pressure, and you're trying to wing a capsule through it at high speeds, and there's a very small gap between the outside of the capsule and the inside of the tube, you're going to end up building up a huge amount of pressure in front of you, and that's going to slow you down. It's going to be very inefficient. So, one of Elon Musk's strategies was to basically drill a hole in the head of the syringe, allow some of the air in front of the capsule to actually pass through to the back and reduce that high pressure bubble in front of you. That allows you to go fast. So what does our capsule end up looking like? You end up having a large electric motor powering a compressor. The compressor takes air into the front, spits it out the bottom for air bearings, and out the back to overcome the Cantor's limit. Elon Musk proposes having, several of these capsules traveling maybe every 2 minutes or so that carry about, 2 times 14 is 28 people. It'd be about 100 feet long, similar to an airplane, and you'd be in a nice reclining position. I don't think any beverages would be served. So why should we do this? This seems kind of extravagant. It turns out it's actually quite efficient. This graph, prepared by Elon Musk, describes the amount of energy it takes to move one person from San Francisco to LA, depending on the type of transportation they use. The big four here, car, motorcycle, airplane, train, the common things we use, take a lot of energy, between 800 and 1,000 megajoules, which is a unit of energy. On the other hand, his Hyperloop takes less than 200, actually less than 100. And another proposed variant of the Hyperloop, which could move cars as well as people, is still quite efficient. Notice how he includes the Model S on there? I wonder if there's some sort of conflict of interest there. So it seems like this is efficient and it's very fast. It's actually quite a good deal when it comes to transportation. But it's more than just a technical reason why. It's not just about saving money and energy. It's about the kind of technical prowess that we expect from California. And Elon Musk actually spells this out very clearly in his white paper. He says, when the California high-speed rail was approved, he actually puts the quotes in there, so you can tell Illinois, I was quite disappointed, as I know many others were as well. How could it be that the home of Silicon Valley and JPL, doing incredible things like indexing all the world's knowledge and putting rovers on Mars, would build a bullet train that's one of the most expensive per mile and one of the slowest in the world? That's the current proposal for high-speed rail. Costs about $68 billion. Will get you the same distance in about 2 hours for a ticket that costs over $100. The Hyperloop gets you there in 35 minutes. The ticket cost would be about $20, and it only costs $6 to $10 billion to create. People look at that number and say, oh, well, all major projects end up going over budget. If he goes over budget by twofold, he'll still come in $50 billion under high-speed rail. So, we figured out why we want to do this. Now we get to the big question. How? It's not as easy as it seems. So let's go through the 4 things that make a Hyperloop a Hyperloop. An evacuated tube to travel in, electromagnetic launch to get you going, air bearings to keep you going, and our friendly continuous limit. So when I first read the white paper, I actually had trouble going to sleep that night. I thought this was a great idea, so I stayed up till like 2 or 3 in the morning writing out my first ideas. So actually I'll reference this sketch as I go through every step of the process. So the first thing we come to is an evacuated tube. How do you get that kind of system? Well, Elliot at 2 a.m. thought it'd be great to have acrylic tubes. Acrylic's a type of plastic that's see-through, so you actually see the capsule moving. That'd be nice, looks more impressive. And you have little sleeves connecting them. So basically you have 2 tubes end-to-end with a sleeve over it, and that'll somehow create a seal. Didn't have that worked out at that point. I'm going to evacuate it by attaching a hose bar. It'll connect to a pipe. It'll connect to Mr. Ruzin's vacuum pump. Seemed like a great deal. I'd just be done. Well, I went through some evolutions. I realized I'd have to be able to take it apart and reassemble it and put it in my car. So it had to be modular, which means it could come in chunks, like Lego. So I ended up with this system of alternating permanent and temporary connections. You have a small tube, permanently connected to a sleeve, that's then temporarily connected to the end of the next tube. So with that kind of premise, I could easily make this arbitrarily long, without much difficulty, and still fit it in my car. Also, I moved the nozzle to the end, and it ended up being much more convenient than drilling into a smooth piece of acrylic. This is one of the first tests that I actually did. Here's Mr. Ruzin's vacuum pump, and here is a 6-foot length of acrylic. It's about 2 3/4 inches in diameter. The most important part of this picture are those 3 white rings you see on the either end. Those are single strips of Teflon tape. It's a very thin and slippery material commonly used to seal threads in your plumbing or in the robotics pneumatics. So that actually creates enough of a seal and stops it from leaking too badly. But with this setup, I can only get down to about 1/6 of an atmosphere, or a 1/10 on a good day, which is still a few orders of magnitude off from where I want to be, or at least where Elon Musk told me I should be. So, enter the FGVP. I found a friend, Mr. Lunday, who works in automation, so we work with vacuums frequently, and he loaned me the FGVP, which is the fancy German vacuum pump. So with the fancy German vacuum pump, I could actually reach higher pressures, or rather lower pressures, and go down to about 1/15 of atmospheric pressure. I connected the 2 because it ended up being kind of slow, and I could use Mr. Ruzin's faster one to just get there faster. But this wasn't quite easy. There were a lot of struggles along the way. Acrylic has really, really bad tolerances. That doesn't mean that it says mean things about other types of tubes. It just means when it says it's 2.5 inches, it can really be anywhere between 2.46 and 2.53 inches. Seems like a small difference, but it can have a huge impact. These two tubes right here fit together too well. They would not come apart after I accidentally and foolishly stuck them together. So I had to clamp it in a vise, and then clamp that vise to the table and really yank on it in order to get them apart. And I realized I'd have problems with this in the future. Other thing you notice, that naturally the fancy German vacuum pump has British threads on it. So, more specifically, they're 1/8 inch diameter British straight threads. And I wanted to use 1/4 inch diameter American tapered threads, which are completely different. And that takes 1, 2, 3, 4 different pieces of brass to make the change. That was a lot of time spent online figuring out what was really going on. At one point, I thought I could probably ditch the Teflon tape for a better solution. This is an O-ring rubber that's managed to fit perfectly in between the two tubes. However, when TAPS plastics touch your tubes for you, they don't do it perfectly perpendicular, it's being at an angle. If you try to seal something at an angle, it's just going to leak all over the place. So it ended up working, and I stuck to the Teflon. In the end, after much difficulty, I had a 18.5 foot long tube that was entirely connected and I could depressurize. So, that took a while to get to. And then we get to electromagnetic launch. At this point, at like 3 a.m., I was totally on fire. I had all these great ideas. I was going to use a coil, right? It kind of works like that. I had no idea what was going on. So I ended up doing some more research, and I found that what I was really talking about was an induction coil gun. So, here you see a nice picture prepared by someone else. You have a coil of copper wire, and you run alternating current through it. That current induces a current in the projectile. Induces is a word that physicists say when they really mean magically creates. So, that current magically creates another one, and naturally the projectile goes winging out that way. It seemed really easy. Obviously, this is bulletproof. Turns out, I ended up with a fail gun. Not a fail gun. So, there was my coil, 10 wraps of 10 gauge wire. It looks kind of similar to what they had. I put a piece of aluminum projectile in it, plugged it into the wall, and the lights went off. Actually ended up I blew a breaker, a 15 amp fuse on the back of the house. So I had to go out, reset that, much to my fair chagrin. And eventually I realized, okay, this is just going to keep happening. So I bought a giant resistor. And that giant resistor is actually like 15 inches long. You work with resistors, they're normally tiny. That limits the current to about 8 amps. Plug that into the wall, no lights turned off, but the thing didn't move. And the resistor started getting very, very hot. It turned out it's also a heater. So what this drawing left out is that you actually need an iron core in order to get any work out of a coil gun. They could have informed me of that. I didn't have time to make one, but ended up borrowing one from Clark and Rohan. This was actually their AppPad project. So I took their coil gun and I modified it a little bit and stuck it in the tube. Therefore I'd have access to it. But again, there were a lot of difficulties. I had to center the coil gun. Like, this thing actually shoots an aluminum ring into the back of the capsule. When I told Dr. Character, he said Rube Goldberg wanted his ideas back. So it is kind of strange. I have it centered with these little acrylic spacers, but when you move the projectile another inch away from the coil, the power goes way down. So I ended up moving that. I also had to get the wires out of the back of the tube while maintaining a vacuum. That required a lot of improvisation and silicone sealant, but I eventually got that to work. And then here's a wasp. No, I did not make it. I encountered it though late at night after I was testing the coil. So 10:30, plug it to the wall, break another breaker, or rather just like flip it. Go to the back of the house, back of the garage, take off the panel, and there's a wasp nest there. So this is not what I signed up for when I found to be doing science. So vegetarians, cover your ears. I did have to kill the wasp for science. So, sorry about that. And then there are the problems with air bearings, of actually making these things. I did some research. On the industrial scale, air bearings are made with micron tolerances. Extremely small distances, very high level of craftsmanship, stuff I didn't really have access to. So I had to figure that out. My first design was pretty cool. It was like crazy, like 3D printed internal structure, like move the air around properly. Like here's the fan, it gets spits out the side and the back, it's gonna be great. Then I realized that if the entire capsule is going to be at the same kind of pressure, I can just drill holes in the outside and get the same exact effect without any fancy 3D printing. So here's my less enthusiastic one-tube system down here, where I just put the stuff in a tube and let it go. finding that tube was actually a real challenge. So here you see a motor connected to a controller. There's a big lithium battery on the back and a little throttle here. So it turns out that the inside of my Hyperloop is 2.5 inches. So I had a tube where the outside diameter was 2.5 inches. And I thought, wow, gee, this is great. And they don't fit together. So that's also probably because acrylic has terrible tolerances. So then I thought, okay, I can get around that. So I want to size down. This is 2.25 inch. And it fits wonderfully. However, my motor does not fit into it. So here I had a problem. One tube was too big, one tube was too small. I ended up searching online and found my Goldilocks tube, which was just right. So I then proceeded to drill a lot of small holes in it to allow the air to leak out the sides. One thing that I realized in this demonstration is that when you have this big difference, there's a huge gap on top. If I simply had my holes and none of those two little white rings I'll talk to you about in a second, all the air would leak out the top, and it wouldn't form any pressure on the bottom, and it wouldn't actually separate off from the middle of the tube. So these are Teflon O-rings. So it's a very slippery plastic, but more important, it's the right size to center the capsule, so that air is actually squeezed around these tiny little gaps, shown right here, instead of actually just pushed out randomly. So in my great idea, the air comes in, it gets squeezed out the sides, small holes, and spits out over the back, and that should make air bearings. Worked for a while until I ran into some more tolerance problems. It turns out that the acrylic tubes that I bought about 2 months later were smaller on the inside than the ones I bought a few months earlier. So the Teflon O-rings do not actually work anymore, so I had to go to plan B. This is 3 layers of polyethylene tape with 1 layer of Teflon tape on the outside. Just 3 layers, not 4, 5 is right out. 3 layers is what you want. And that ended up working with a little bit smaller. Even that wasn't particularly easy. I had to drill a lot of small holes. I ended up damaging the fan after repeatedly whacking into the end of the tube. And it actually pushed itself so far into the capsule, I couldn't get the department to take up the battery. So then I clamped it in a clamp, clamped that visor, and then had to yank on it. See, it's kind of like a repeating image here. And then there's the cantor's limit. I'd say this for the end. It was definitely one of the most challenging things I did. I drilled a hole in the back of the capsule and it worked. So, I'd like to show you a quick test. Here is a brief picture. You see Mr. Wisden's vacuum pump, the FGVP, the tube, and there's a coil gun at the other end. Here we have the first test of the full Hyperloop. Right now the vacuum pumps have taken out 20 inches of mercury of pressure, so it's about 1/3 of atmospheric pressure. I'm going to turn on the capsule with remote control, and then hit the coil gun to give it an initial boost of energy. What you may have noticed is that the capsule started moving before it was hit by the coil gun, and then continued to accelerate. That's because on a good day, the coil gun might deliver 1 joule of energy, and the motor will deliver 150 every second. So at this scale, the compressor fan can definitely power it, although it wouldn't actually work if you're trying to do it at a large scale. But you know, what kind of stuff does apply? The lessons about material tolerances. If you want to make a tube that's 350 miles long, and you want to have air bearings in it, you're going to have to make sure that the entire thing is very uniform, which can be very expensive. So I was using extruded acrylic. They literally melt a bunch of plastic and squeeze it out of a ring-shaped hole. It's like Play-Doh. And it kind of melts and solidifies roughly the right shape. That's really cheap to do, but you get bad tolerances. If you wanted to cast it in a giant mold, you get better tolerances, it would be much more expensive. So the material choice of the pipe could actually be extremely important. I assume they're going to be using steel, but actually how they make it could be the real problem. Mr. Wisden pointed this out to me. Everything expands when you heat it up. So if you take a piece of steel and you heat it up 1 degree Celsius, it's going to get 1/1,000,000th of its length bigger. Doesn't seem like a big deal. Turns out, if you take 350 miles of steel and you heat it up 20 degrees Celsius, that's like a big swing from day to night in the Central Valley, it's going to get 480 feet longer. So you're walking to Caltrain, And some of your Caltrain stations 2 blocks that way because the rail is there. So obviously there is a way around this. The rails actually have little gaps in them that expand on a hot day. That's actually where you get the clicking noise as you go over the tracks. Bridges will have similar expansion joints. But here's the thing. You can't have little gaps in your tube, otherwise your vacuum is not going to have a seal anymore. Also, if your air bearing hits that little gap, maybe it'll lose pressure and then it'll leak. So that could be a huge problem. Holding good tolerances over a long distance while maintaining a seal doesn't have much of a precedent. The thing that comes close is oil pipelines. I mean, they do cross continents, and they do obviously heat up and cool down, and they do actually maintain a seal and hold this, dangerous liquid. However, the tolerances on the inside of the pipe don't really matter. Oil doesn't care if it goes over something that varies by a few hundredths of an inch, as long as it's slippery. So, that's what I think could be the biggest challenge that people actually making this could fix. So, with that, I'd like to thank some of the people who helped me make this possible. Mr. Wisdom, a great mentor. I highly recommend him to juniors. He keeps me on track. Mr. Patterson, kept me going when things got rough. Dr. Carricker tolerated my presence when he was trying to grade papers, so I'll thank him for that. Mr. Lunday found me the FGVP and actually encouraged me to try out O-rings. And then my parents let me put a 20-foot long pipe in the living room for a few days. Not too many complaints. Elon Musk, total boss, came up with this idea. The internet taught me how to do it, specifically Wikipedia. And of course, viewers like you. Thank you. Any questions? Mr. Wadley?
You talked about why and how. I wonder if you thought at all about where and whether this would, if taking the route for the high-speed rail, for example, would that be a good place?
I didn't have too much time to spell that out, but in his white paper, he actually details a very specific route. Mostly it would be on the I-5 Meridian strip. You'd actually have pylons in the middle of the highway just going up, and you'd have it all in the air. So you wouldn't actually have to do any sort of eminent domain taking a bunch of land. Right now, high-speed rail needs to take a 100-foot swath down the entire state in order to put the tracks down. And this would only take, 5 feet, because most of it would be in the air.
How fast would it accelerate? How's like that?
So that's one of the things. Elon Musk spells out that you don't want to be accelerating at more than 0.5 of a g at any one point. Otherwise, it gets very, very uncomfortable. Still, 0.5 g's is quite a lot, so it's going to be less like a comfortable airplane travel and more like a roller coaster ride. Yeah, so limiting acceleration is a problem.
Could you put loops there? Like a roller coaster?
Jesse?
Yeah, so is there going to be like some really huge earthquake in the next 20 years in San Francisco, like a 99% chance?
That's a good point to bring up. Elon Musk definitely talks about that, and he says that all these pylons that support the tube, they're going to be able to flex in all dimensions. So in order to account for an earthquake, the entire thing might go sliding back and forth. That's actually built into the system. Granted, yes, that still could be catastrophic, but it also damages roadways and railways just the same. So it's kind of vulnerable. Goodbye.
As designed, it looks like it's a point-to-point system. Is there a way for interim access points?
So, that is true. The main stations will be at the endpoints. He does specify an alternative route that would go outwards, but for the most part, he actually does not say that we want to have in-between stations, just for convenience and make it very difficult to accelerate, slow down again, and then accelerate. But if there was a major population center that wanted to have that connection, I'm sure it would be economical to do that.
What kind of noise level is this thing? Is it going to be really noisy or no?
So from the outside, you won't hear anything because it's under low pressure and there's going to be very little sound coming from it. On the inside, it uses a giant electric motor, which is pretty quiet, similar to what they have in the Model S. So I don't think there's going to be a huge amount of noise. Not like an airplane. Cool?
What about security? Like when you go to the airport, you have to go through security and
Yeah.
how would that be like, you think?
So I imagine that carries some similar risks. People have figured out how to do that for airports, so you probably have to do the same sort of screening process before you get on the Hyperloop. Again, just like being in an airplane at high altitude, being in this evacuated chamber is a dangerous place to be. So yeah, I'm sure there'd have to be security at the endpoints, much stronger than a normal train.
How does it decelerate?
How does it decelerate? It turns out, here's actually one of the coolest parts, the same linear induction motors can take energy out of incoming capsules and store that in giant batteries to be used later to accelerate other ones. So same system can take energy out of it and slow it down nicely.
How many of the capsules would be in the tube at once?
I think they depart every 2 minutes. So if you count for both ways, it's about 30 capsules at a time.
Is going from San Francisco to Los Angeles like as popular enough like transit that they would be worth doing?
Yeah, Elon Musk estimates there's actually 6 million people making that trip annually, and most of them do end up flying or driving. So there actually is a fairly big market here, because you just want to find 2 major population centers a few hundred miles apart.
So all these, like you could, every 2 minutes, there's this big group of cars that all go at the same time of these things. And then they get at the end, what happens there? I mean, it's like there's going to be this backup of...
So they're not trained like that. It's not like cars in a large train that go at once. They're individual capsules that will depart every 2 minutes. So that 28-person capsule will be independently.
Oh, and then what happens when it gets to the end? Where do they go? You know?
Yeah, it is a two-way system. So the same capsule would end up being able to go both back. It doesn't go back. That's actually something that people need to figure out. Like in the capsule, it needs to go at some point, it's going to have to stop being in the low pressure zone, turn into a kind of station where people can get on board, and then leave again in the opposite direction. They do that for trains. They have these big wheels, so I don't think it would be as challenging as some of the other problems that we're dealing with.
Yeah, so God forbid, if a system like this were to be damaged, and how dangerous would it be for the passengers inside, and what does maintenance look like for like weather or terrorist threats?
There's always challenges. Elon Musk says that capsules should have emergency systems, wheels, just in case they can get stranded in the middle. There would be emergency access along the tunnel, but that is actually a major concern. I think if you go out of there, it's going to be close.
That's our time, unfortunately, for coming in. Thank you very much.